Hello, Adam. Remember, I like the interaction. It's more fun. and I can't force you to sit closer, but I can tell you have already. But yeah, I'm going to start here. 'Cause the demos are starting, so you can see better. It'll be cozier in the future. You don't have to. You can move now, but I like you down closer. So if you're not one of those that it doesn't bother you, come on down. So, some more logistics. I'm Adam Beehler. This is Physics 1010, the way things work. Some people have added that weren't here Monday. So briefly, yes, you've missed, 2 homework assignments have started. An intro that goes over the syllabus and class logistics, and a second one that starts with chapters 1 and 2, about science and Newton's first law. They are due Sunday through an online homework system called WebAssign. Those of you that are new and don't know what I'm talking about, I've changed Canvas, so there is this course in Canvas now. It was for a logistics reason having to do with clicker integrations. So you can get to the WebAssign link there, or through my syllabus, or what I gave you last time, or go to the physics homepage under courses. It's on the left, and that'll take you right to WebAssign, log in. Once you're in WebAssign, then you can see those assignments, the due dates, calendar, syllabus, all the stuff you want to know about. So if you're new to the class, go into WebAssign and read everything, and you'll be caught up. If you still have questions, of course, then ask me next time or email me. Let me show that again real fast. Some of you might have had issues and others not. So let's see. Open the internet. So I'm going to go to the physics homepage. Over here on the left is something called courses. See how I circle it lots? I'm proud of that. Everybody, go here, and you were looking down, and now it's 2 pages later. No, it's over there on the left. We're at the top, the way things work there. So you click on that, and that gets you to WebAssign. You can also just Google WebAssign and get to Utah's login. Because if you can't get past this stage, you'll have issues. So you enter your university ID and password, and it'll take you to a page that looks like this. And the key there is it says, you need to purchase something. You will need to, but right now there's continue my trial period at the bottom left. You can click right here. You have 11 days remaining to use this free to get in to see what you need to see. After that point, you will not be able to have access to anything until you purchase an access code. And yes, you will need to purchase an access code if you want points. So, important things that you should have found out about by now. Here's the 2 assignments. You can open them up. Let's do like this first one. And it'll tell you the point values up here. Tells you when it's due. You can ask me a question right here. You can print the assignment and work on it offline. Friendly reminder of a description. I added this description that, like on this one, there's 4 options. So by default, I typically say you get 3 chances, but you're going to lose half the points every time you get it wrong. You can click on this and learn more info. Tells you stuff. You can submit just this answer, or you can save your progress and work on it later. Or once you're all done, at the bottom, you can submit the whole assignment at once. Or just save it for later. You just have to make sure you've submitted it before the deadline. I think the default is if you've saved your progress, wherever you're at come the due date, it automatically submits it for you, but you might not be done. It's always best to hit submit and ensure that you've submitted it. So you can do that. So there's those 2 assignments. Other than that, here's the info about this class. There's a schedule when we're going to be having lectures and things are due and exams. There's a syllabus. Here's a paper that's being assigned that'll be due in April, and you can read all about that. Some of you might have read about that. Any questions at this point about that? The superhero paper? Okay, who read it? Okay, nobody read it yet. All right. All right. Well, if you have questions anytime on this stuff, just ask me. Yeah.
The bookstore ran out of clickers, but the kid over there told me they don't have them by Friday.
By Friday? Okay. I won't hold it against you. I was going to try some out today for those of you that got it, and you can see how it works. But I'm not counting. I didn't intend to count any points this week because of this. I'll start next week. They're for participation. You'll get a point for participating. And some of them you'll get points for getting it right, too. To encourage you to not just guess and actually study, you know. Also, over here on the right, on the announcements, there's our TA with her office hours. She's willing to help you. And the video. You can see that the lectures get videoed. I don't know if anybody's looked yet, but I posted the URL there in YouTube. And so a day or two after each one, they should be posted. Things are going normally, and you can review. Those will be there for you. So those of you that weren't here the first day, you can go watch that whole wonderful lecture. Questions? Concerns? Shall we try the clickers out and see how that's going to work? All right. Go ahead and pull out your clicker or responseware, mobile device. So what I do is, up here on the right, I click to connect to responseware. I say log in, and it gives me a session ID number. I can close that, don't fret yet. I do polling. And here, this window shows what channel your clicker should be on. I'm using channel 44, so you need to adjust your clicker to be channel 44 through its menu. Give you time, don't worry. If you're using a mobile device, there's your session ID number that you will need for this lecture. It'll be different next time. And then everybody would be logged in, we're connected, and I can ask you questions. Looks like people are connected. Anybody not on the right channel or session ID yet? All right, and that's how it works. Like, here's a question that we discussed from Chapter 1. So I open the polling, and you guys should be able to respond now. 2 people have. 4, I can see. And so can you. We'll see how many it's working for today. Now, I'm just double checking. Is this screen being shown, or should I get in the habit of reading it? Because it's not.
You should read it, but it is going to be shown.
Okay. Person who says, that's only a theory, likely doesn't know that a scientific theory is a what? And the choices are a guess, a hypothesis, a vast synthesis of well-tested hypotheses, or a guess that may or may not be true. Factual, I should say. Let's see, we got 12 people. Raise your hand if you're trying to submit. Get an idea of. Okay, we probably got everybody at this point. Those that are trying, did it work? Anybody it not work for? That has one or is doing it yet? All right. Oh, we gained another person. So if I hit stop, it shows the responses. Most people think it's C. And it is. You're correct. So point here is, a lot of people, remember the theories in the normal world think, oh, that could or could not be true. They're just making it up at this point because they don't know any better yet. Well, in science, no, it's really well-founded, based on lots of laws and principles and facts put together. And that seems to describe all these relationships wonderfully. Granted, if we learn more info, that could change and adjust. But for now, it's the best thing we have that works really well. And it hasn't been contradicted yet. Questions about the clickers and things then? Yeah?
Question. Do we have to register it through Canvas or Clicker?
You can now, but it's the same registration. So I gave a link in my syllabus. You go here to register your device ID, which is right on the back of your clicker. Or if you're using ResponseWare, you'll be emailed an ID number for your iPhone, iPad, laptop. You'll have to register that ID number on that link I gave you. It's just now there's a module on our Canvas page that takes you to that same place to log in and register your ID number. That's so I can contribute points to you. I know who has what device. Well, let's do another one. Where's my... Okay, I open polling. Now, if you don't have your clicker right now, are you at least committing in your head what you think the answer is? Give me some nods. Okay, good. So, more important than a test for proving a hypothesis right is a test for what? Knowing it's full well right, proving there's more than one way, proving it wrong, or elevating it to a theory. And I can go, you have 10 seconds left. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. All right, so see, we can see that most of you think it's C, but some of you think it's D. The correct answer is C. It's more important that to be able to prove it wrong, because then you can definitively say, yeah, that's not right. Because there's lots of things where it's you don't always know. They're kind of open-ended. The hope is to eventually turn it into a theory, but that's not what's important about a hypothesis. So here's an example. I'll open up the polling, see what you think. And I have to remember, these little boxes went away last time I did this. Now they're staying on top. So which of these is a scientific hypothesis? Which one can be proved wrong? What do you think? Hopefully you're running through these, clicker or not, and asking yourself, can that be proved wrong? Ever? That's all the responses we've been getting, so I'll go ahead and stop the polling. A and C people are going between. It is C. An atom is the smallest bit of matter in a material. That actually has been proved wrong. Because we have found electrons, protons, neutrons, quarks, subatomic particles. And so, yeah, that one can be and has been proved wrong. Let's look at A. Atoms in proper proportions make us feel good. It's too subjective. It can be proved wrong maybe for you. Okay, yeah, it doesn't make me feel good, but it makes you feel good. So how do we distinguish which is right? Well, you can't. So it really can't be proved right, and it can't be proved wrong. That's just subjective. B. Atoms are in all the stars in the universe. We can go to stars and check some out, but can we ever see all of them and know for sure? No. So it can never really be proved wrong, at least realistically at this point. And D is distant galaxies have atoms not found on Earth. We can go to some and might find some, but we can't hit everything, so we don't know for sure. Anyway, you get the idea? Yeah.
I have a question about the first question you had.
The first one, yeah.
When does that tip over into becoming a law?
A theory?
Mm-hmm.
Theories are actually based on laws. I remember it this way. Facts are like little pieces. They were, people observe  about something, like the world is flat. And that became a fact. But of course, what I want to emphasize is that can change, but that's just about one little thing. Then a law or a principle is based on several facts. It's kind of a general hypothesis about the relationship between several things. Whereas a theory involves all of these and many of them, several hypotheses and facts that have been well tested and well verified. So if that helps you, facts are kind of smaller, laws and principles a little bigger, more encompassing, and theories even bigger still. Does that help? Not really?
Too much.
What's the confusion? Help me out.
I guess I thought law was on top. Theory was in the middle.
Oh, well, now you know. And it explains this again in chapter 1, and there's a glossary. It defines them. So you can review that. But yeah, in science, that's how it works. We pick little facts, kind of like observations. And if that seems to work a lot, we make a law. Like Newton's first law, which we're going to get to now. It seems to describe a relationship between matter and its mass and its resistance to want to change motion. We seem to observe this a lot, so we made it a law. And that law is part of a theory that we have on motion and forces that encompasses more than just Newton's first law. So, okay, let's turn this off. Or just mute it. Groovy. So that's how that'll work. I intend to ask questions like this, like we've kind of gone over them. These would be kind of like check your understanding. Because ideally you would have had a chance to go over this in the textbook by now, and we had a lecture on this, so are you getting it? If these are still confusing, then there's an indicator for you that, I need to cover that a little better. I'll also ask some prediction ones, or maybe some teasers that we're getting into. And when I do some demonstrations, I might ask you to predict what you think will happen. You'll make your own hypothesis. So, anybody know what Newton's first law is? Inertia. That's how I like to define it. Who's heard of the word inertia before? Yeah, not everybody. It's typical because it's not a normal word that we use all the time. Inertia. How would you describe inertia? Anybody want to take a stab? Either you've already studied it or happen to know. Going for it? Thanks for being brave.
I'll try to remember. Isn't it when, like, even when the force is stopped, the object just continues to move?
Yeah. Even when the force is stopped, the object continues to move. Good. What else? Anything?
It's a tendency to keep doing what you're doing.
Tendency to keep doing what you're doing. Yeah, that's more general, but yours would fall under that. So I'm going to add to that, tendency to keep doing what you're doing. Inertia is kind of like resistance to change. That's the shortest way I can sum it up. You can have the official definition from your book. But it's basically, something doesn't want to change. They say sluggishness. So yeah, that's why I like Hewitt. He uses normal words. Well, some of the time. Sluggishness, or apparent resistance of an object to change its state of motion. You can also think of mass as a type of measurement of inertia, because they're related, inertia and mass. What's mass? Recall your chemistry, maybe.
The amount of space something takes up.
The amount of space? Good, that's to it. I would call that more volume, but it has to do with it. It's how much matter, it might be a more accurate way, something has, which is directly related to how much space it is. But we're going to cover density, by the way. Density is that relationship between matter and volume. Because you can have a lot of matter in a big space, or the same amount of matter crammed into a small space. And that will affect the density. But that's later. So yeah, mass is kind of like how much matter something is, how much substance is there. And it's a measure of how much inertia it has. And now we know inertia is this sluggishness or apparent resistance to change its motion. Thus, this is at rest. Now, this is more fun. That's at rest. So it has a certain amount of inertia. So if we try to change its state of motion, which is at rest, it's going to resist. And that's why when you push on something, you feel it. You know, you have to work a little bit to get it moving. This is lead. This is 26 pounds. Do you think it has more or less inertia? You're right, more or less mass. More. So, it's harder to get it moving because it's resisting me more. It has more inertia. Now, which one would you rather catch if I throw it at you? That?
We're calling Adam.
Are you prepared?
I'm prepared.
Okay. I wouldn't do that. I think you get my point. You'd rather catch the block than the lead. Why? It's easier to stop. This one. And that's because once I throw this, that's its state of motion. It's moving. So that's part of inertia as well. It wants to keep moving. If you try to stop it, you're trying to change its motion. And so this one's harder to stop. So things at rest want to stay at rest, and things in motion want to stay in motion. Until what happens? Very good. Until it's acted upon by an outside force. I mean, if you want to move something, you got to push on it. If you want to stop something, you got to push on it. That's Newton's first law. Now, I find that most people, I would think you're going, yeah, that makes sense. But as we start to apply it in the next several weeks, you might find some confusions, and so we'll work through those. I want to clarify one of those confusions right now. A lot of people... Oh, yeah.
So friction would be an outside force, so it's like something's moving. Friction would slow it down and stop it, right?
Excellent. Friction is an outside force. Galileo, the reason I like him a lot was a lot of people did talk, the theorists in science. Oh, it's explained like this. Well, Galileo just went out and did an experiment. And one good experiment can correct decades, millennia of theory. It's like, well, let's see what happens. He goes and does something. Well, no, it's like this. So you're wrong. And once it's understood. And that's what he did and helped us understand this. What do we observe? When I slide this, it doesn't keep going. I thought you just said things in motion want to stay in motion. That's not what we observe. Because what's happening to the block?
Gravity.
Gravity and friction are both acting on this. And if you don't realize that, you think, oh, well, things want to just come to rest, earth with earth. Well, no, the real rule is things in motion want to stay in motion unless an outside force acts on it. Well, an outside force is acting on it. And in our lifetime, in our world, there's always something that seems to be acting. Friction. Let's get rid of friction then. Here's a hover puck. It blows air out the bottom, so it minimizes friction. We'll do it on the floor. So it's moving, it's happy. It doesn't slow down. Newton was right. If it's at rest, it's happy. I have to exert a force on it to get it moving. But once it's moving, it keeps going until something acts on it. And in this case, it's not friction. Okay, now it is because the batteries just died. You can go slowly, but you get the idea. Or until it runs into something, and then that exerts a force on it to change its direction. So, excellent point about friction. On my bucket list, I have a short one. Some people have pretty long ones, but one of them is I would like to chuck something out in space someday. So what do you expect to happen? You take the baseball and you just whoosh, what'll happen?
At the same speed.
Yes and yes. Until something else happens to it. Yeah, so it'll keep going at the same speed, with a straight line, forever, until something acts on it. But out in open space, there's not much to act on it. If it comes near a planet, gravity will start changing its direction. But yeah, it'll just keep going. At that same speed, forever. So, you're in a car, going 55 miles an hour. No, this is Utah. You're going 85 miles an hour. All right, and constant. 85. You're consistent. 85 miles an hour. Is your motion changing? Is your motion changing? Are you committing in your head? Give me some head nods. Straight down the highway, maintaining 85 miles an hour. I'm hearing more no's than any yeses, so correct. You're at a constant speed. You're happy. You're not changing. What's propelling you forward? Why are you moving forward? Inertia? What do you think?
Force.
What force?
The engine?
The engine?
Yeah.
Okay. The internal combustion engine driving the drivetrain gets to the wheels push on the ground pushes back. Yeah. Okay, that propels you forward. Why aren't you going faster? I mean, there's a force pushing you forward, but you're not changing your motion. See, I thought forces change motion. But if you're staying at 85, are we wrong or is something else happening? Okay, I heard air resistance. What else? There is a balance of forces. Air resistance is one, pushing you the other way. What else is pushing on you? Gravity's pulling you down. And friction. Yeah, inside the engine, on the ground. And so there's a balance of forces. So you have your car. And yeah, your engine ultimately, it's propelling you forward. But if there's a force pushing you the other way, or a combination of forces, and those are equal, then there's no net force. The net force involves all the forces. So if you have F1 pushing you to the right, but you have F2 pushing you to the left, so we say it's negative for opposite direction, and those are equal, the net force is 0. So we're going to talk about net forces a lot. And that's why you don't change your motion. Forces are balanced. And so what I really want to emphasize is, it is not inertia that keeps you going. Or don't think of inertia as a force. Let me put it that way. Inertia is not the reason you're going on. It just describes that resistance to change. But get out of the habit now before you get going into this. Inertia is not a force. It's just kind of a property of matter. It's the best we can explain it. To explain this resistance to want to change our motion. So to make this, to change going 85 miles an hour, we can do two things, right? We can slam down the accelerator and go faster. That increases this one, doesn't it? So if it's bigger than this one, then you're going to have a net force propelling you forward, changing your motion. But if you put on the brakes, you're going to have more resistance, more friction. So this one will be bigger. And so you'll actually decelerate. You'll slow down. That's a change in motion. But it wasn't until there was a net force on you. Okay.
Quick question.
Yeah.
If there's no net force, how is it moving? I guess.
That's because you have these two forces in balance.
Yeah.
And once you get moving,
Okay.
we like to say inertia keeps you moving. But it's not a force. I mean, we say that. It's not the reason. It's just that's Newton's first law. Things in motion want to stay in motion. So if you're moving at 85 miles an hour and everything's in balance, you're happy, and you'll just keep doing that forever. Until some force comes along to change it. But quite often there's more than one force going on. See, these examples, it's just sitting there, it's happy, horizontally. I push on it. Oh, now there's a force that moves. But here you got two things going on. And so you have to look at the net force. The combination of everything happening to that object.
So when it took off,
There, this had to have been bigger
there you go.
to get it to move in the first
At
place.
some point it got,
Then they're balanced, and we're happy again. No net force. And you just continue like that forever. Another example is an elevator. A lot of people think that one. You hop in the elevator, you hit the up button. That requires force to change your motion from rest, right? So you get moving. But then you actually go at a constant speed. Up. You know, you don't feel anything. That initial, whoa, and then you're riding along. And that's another example where you got something pulling you up, but you have resistance and gravity, and they're in balance when there's no net force. And you just continue at a constant speed in a straight line until something else happens. At the top, when you stop, and this one becomes bigger than this one. Again, a net force causing a change in motion, and you resist that. And you, whoa. you know why you feel like you go up? It's because you're moving with the elevator, right? You're both going that speed. If the elevator stops, why should you keep stopping? Inertia wants you to keep moving. So you kind of go, whoop, until gravity acts on you and you come back down. Just like in a car with the purpose of a seatbelt. Yeah.
So what you're saying is if the net force is zero, whatever motion they're in, whether it be stopped or moving, it's going to stay constant. But if it's a negative or positive, it's going to accelerate or decelerate in whichever way.
Absolutely.
Okay.
To reiterate, if this is zero, constant motion. There's no change in the motion is more accurate. So if you're at rest, you stay at rest. If you're moving at that speed, you stay at that speed. And forces can act on you in either direction to change that. But it won't change until you have a net force. Let's do this. That's one of my demos here. Let's see. So you got your car. You're happy. All right, you're in it. And somebody takes off really fast, right? You're in a rocket car. What happens? Well, you're at rest. So is this. So it takes a force to move you. I push your car, and so it resists, but it starts moving. It changes its motion. Well, there's some friction between it and the car, you and the car, the seat. And so it's trying to propel you forward. But you resist that, and so you want to stay put. That's inertia. So when you feel like something's throwing you into the back, pushing you into the seat, that's just because you're trying to stay put. Your inertia, you're resisting that change. Now you're cruising along with the car at 85 miles an hour, right? Ah! That's what happens when you don't wear the seatbelt. You're with the car, this stops the car tries to stop you, but your inertia says, And so you continue at 85 miles an hour until some force stops you. You don't want that to be the steering wheel or the windshield. You want it to be the seatbelt. Okay, show of hands. Who's ever tried pulling out a sheet from underneath? All right, keep your hands up. Of those with your hands up, put your hand down if it worked. Also, some of you didn't work. And who's ever always wanted to try it, but were then afraid because you thought you'd break it? Really? You wanted?
Yes, sure.
Come on down, and today's your day. We're going to make it happen for you. And before I have you do it, I'll give you some hints. Give everybody some tips and hints. All right. Tip number 1. This has inertia, so the faster you try to pull it out from it, the better. I mean, if you just pull slowly, it has time to react. So if you can do it fast, then they should resist better.
I'm afraid it will be broken with this.
I can go back to DI and buy a new plate. It's okay. So go as fast. You have to commit and go fast. To help you do that, I suggest you bunch it up like this, but leave a little slack. Some people start way up here and they start moving. But as soon as you start moving, so is this. And so you start slower. If I'm like this, by the time it starts sliding underneath this, you'll be at a higher speed. So it'll be even faster. So if you start like this and then it'll be going faster by the time it starts really moving. Tip number 2, go down. Most people want to go like this. They get all excited and go, wah! Or they pull up. No, you don't want an upward force. We want a sideways force. So if you go down, it'll slide right underneath it. Tip number 3, cut the seam off. This one does. But if it hits the seam, then that provides a force upward and messes things up. So here, go ahead and grab it. Get ready. We'll get you going. Here, let's make it harder. Just add more stress to your life. Okay, let's see. How much slack do you have? Slack, slack, slack. There, now come forward. No, don't. Just with your hands like this. And you're going to go down, right?
Yes.
Don't run. Okay. Are you?
Grab this?
Nope. That way, by the time you get here, it'll be moving faster. Okay, are you ready?
A little bit nervous.
Start up here.
Here.
Yeah. Give her a drum roll. Don't go up. Whoa! All right. That was a good first try. All right. Hey, no, you get to do it again. We're going to teach you how to do this.
You can change another one, I guess.
Oh, no, you can do it. No problem. That was a great catch, by the way. Go ahead. Grab it again. Get ready. What my suggestion for you is, I think you chickened out. Once you start moving, just go for it. Wah! Really fast. Okay, down. That's good. Start up here. Start up here. Okay. Yay! Good job. Now, see, you have success. You can say you did it. And now all of you can go home and try it. Now, you guys are good scientists. I know you made observations. Tell me some things you noticed that happened in our experiment here. Things you noticed.
I don't know, for me it seemed like the things that were heavier had an easier time staying put.
Good observation. What else? The heavy things had an easier time staying put. Anything else?
Because of the various substances of the different objects, some of them slid a little easier and stayed put, and other ones had more drag.
That's good. Nobody's ever mentioned that before in my classes. The amount of friction between the materials varies too. Yes. Did you honestly get scared when I poured the drink?
Yeah.
That actually made it easier for you. Because these two things are heavier, which means they have more mass, which also means they have more inertia. And inertia is defined as a resistance to change. Very good. So these want to resist you more, thus it was easier. They wanted to stay put more, so they didn't move as much. Where the less massive objects had less resistance, and so you heard them bouncing around more. That's Newton's first law. Things at rest want to stay at rest. But remember this, more massive things are less affected by the same force. That's basically Newton's second law. That's the next 2 chapters. We'll come back to that. More massive things resist that force. So they have not as much change of motion. Newton's first law leads right into Newton's second law. Let's see, where are we at?
Quick question.
Yeah.
To the elevator scenario. So when an elevator stops, your body doesn't really lift up the ground, but you feel it in your guts. Is that because your guts are less mass or like easier to move?
Yeah. You got all your organs in here? So yeah, if you're all moving up with a certain force, Well, it's balanced. And you're here. At that point, you're happy. Right? But you got to stop. To stop, which one's bigger? Yeah, so. By the way, I'm going to pause. These are called force body diagrams. When you start drawing force vectors, I'll be doing that a lot. And I encourage you to draw pictures on these. It'll help you realize what to do. If you ever get to a problem and you're like, huh? Well, draw a picture and start drawing the forces that are on it. And most of the time it becomes more clear to folks. Oh, right, okay. So, if this is bigger, yeah, now we have a net force down, don't we? The length of this is proportional to the magnitude. So this force is this big. This force is bigger. So the difference is roughly to scale. There's a net force downward. So they give direction and magnitude. That's called a vector. We're going to be using those too, so I might as well just tell you now. Vectors include direction and magnitude. Does that make sense? We'll revisit this. And it's defined in your book. So, that causes us to change our motion that we were happy with. The elevator stopped, but you want to keep moving like this. But you don't like fly into the air. But your internal organs are moving with you too, right? And maybe they're not clamped down as strongly, and so they start shifting also. And that's why you can feel it. If you feel queasy and weird, and the fluids in your ears start moving, and you're like, huh? And that's why people wear helmets. Because if your head's moving, and you run into the wall, your head stops. What's your brain want to do? Keep moving, and it gets slammed into the fluids in your skull. That's not good. Helmets will help cushion that, and we'll discuss that more when we get to chapter 6-ish. Good question. All right, let's see what I'm leaving out here. That's pretty much the concepts behind chapter 1. Let's do some more demos, and next time I'll do some examples, more pictures like this, maybe throw in some numbers. Okay, here's one. Let me come over. This brick is 26 pounds. It's heavy. If I put it on my hand, this is not comfortable because it's heavy. But if I hit it, that didn't hurt at all. Anybody want to try it? Do you? Come on down. So what's happening now? It's heavy, so just the fact that it's on there shifting around a little, that's not comfortable. But the swinging and hitting it, why he's coming down and setting up, why? Why does it not hurt me more? So my only suggestion is have your hand cupped slightly. Get it under there, help yourself so that it's comfortable-ish. And you might start out tapping and then work your way, whatever you're comfortable with.
That's crazy.
Why is he not dying? Here, wait, stay there. Are you ready? No, I'm just kidding. Thank you. Why? I'll help you then. Why would it hurt?
There's a lot of force going into it.
Yeah, we're exerting a force downward on the hand. It should push it. It's trying to change its motion, right? Yeah, you think that would hurt. So, yeah.
Isn't it like, being stepped on in like a boot versus a high heel where the force is dispersed over a larger area?
Very good. She says like being stepped on with a heel of a shoe versus a boot. That's part of this. It does spread the force out over a larger area. If we just did this, yeah, well, that would hurt for that reason too, because there'd be more pressure, force over a smaller area. And we're going to talk about that later too. So this does spread the force over a bigger area. So your hand feels less pressure. However, that's not the main reason it didn't hurt.
Because of the brake's inertia.
Bless you. It's the inertia of the brick. It has a lot, doesn't it? So the hammer's trying to push the brick. The brick's what's pushing your hand. The brick doesn't want to move because it has a lot of inertia. You hitting it, you're applying a force trying to change its motion, yes? But it resists that better than your hand does. And so it doesn't move easily down into your hand. And so you're not feeling much added force pushing your hand because the brick absorbs most of that from its inertia. If you did this with something light, like this, I'd be in the hospital now. This one. These are good party tricks. Let's do this one. You put a cardboard hoop. I cut it out of an oatmeal container. So, with my magic abilities, I can have this dropped right into the cup. Yeah. Okay, who wants to try it? Yeah. Due to time, I'll give you the punchline. You have your friend now try it, and they come up, and 99% of the time, they're going to whack it right here, and it's going to go flying. Because this thing flexes. When you hit it here, it applies an upward force to the cardboard and pushes it out of the way. So what I did was, you fake them out. You act like you're hitting it here, and then you go and pull here. Yeah, because when you pull here, it flattens, slides right out from underneath the coin. And what does inertia say? Things at rest want to stay at rest, and then gravity takes over. Falls right in. That's fun at party tricks. Or you can try it with a certain length rod. I've seen people do this between bottles. Put a dollar bill between the bottles. I've done that before too. And see, I'd have more people come up and try this. We're out of time. So I'd bet money none of you could pull this out fast enough like this. I've practiced. But I'm serious, I would bet money. But here's your trick. Let's do it like the tablecloth. Tip it a little there. And then karate chop it. You can always go faster. And then it doesn't fall over. Here's a practical use. We don't make wood hammers as often anymore, but the heads are just slid on there and they're kind of friction tight. But how many have used a wood hammer and the head becomes loose? What did they teach you? How to make it tighter?
Hammer nails into the top.
Yes, you can hammer nails into the top, which I've done, because it spreads it out and creates more wedging. But a simpler way is you can just slam the hammer down like this. Like this. There's my makeshift, so you can see it better. See what happens to the head? Inertia. You're moving together. This stops the handle. But what does the head want to keep doing? It has inertia. And so you can wedge it back on there tighter. Watch this one, though. What if you hit the top? Start in the middle and see what happens. By hitting down on the hammer, I can make the head go up. And the last thing I'll say, because I know time's up. If it's here, I'm hitting the handle down. But what's this want to do? Its inertia wants to keep it put. So the handle slides down, and the head tries to stay where it's at. But now it's in that position. You hit it again, and now it's a little higher relative to the handle. But that's all inertia. All right. See you Friday.